Today, we want to review once again the other big question in calculus. The first big question that we dealt with this derivative business was, what is the slope of the line tangent to a curve at a given point? And big question number 2 is, what is the area under a curve and above an interval on the x-axis? The big idea is that we're calculating area. Area is length times width. The length in this scenario is continuously variable. That's the problem. We can deal with variable by just dropping back to addition, but we have to find a way to deal with continuously variable. The way we deal with continuously variable is to take out the continuously parts. One of the 3 great tricks in math is just do a simpler problem. Look at what you're dealing with and do a simpler problem. So the idea is that we flatten out the function for some small change in x. Then we get to use multiplication, and we just add up a bunch of rectangles. So we take the height of this rectangle, the ith rectangle, and we multiply by the width, delta x. And we do this for a bunch of rectangles, and we add up those areas. So this is an area of a rectangle. That summation is us adding up the areas of those n rectangles. And then we do the calculus thing. This was continuously variable, so we use an infinite number of rectangles. We know we're not supposed to plug in infinity, so we write limit as n goes to infinity. That's how we plug in infinity. Y'all don't get to say that now because you're Calc 1 students, so you can't be like, oh, plug in infinity. But after you finish Calc 3, you can be cool and be like, oh, we'll just plug in infinity. And everybody be like, oh, yeah, that's the way the cool kids do it. You don't get to be cool kids now because you're just starting out. This is where we get our Riemann sum. Then we get to the mechanical bits that we spend a lot of time on in calculus. This becomes the definite integral over the interval from a to b, the definite integral from a to b of our function. And at this stage in the continuous sum, the delta x becomes the infinitesimally thin dx. This is our definite integral. We can think of the definite integral as a continuous sum. The Riemann sum is the thinking behind this definite integral. The Riemann sum starts off as a discrete sum, and it's acting as a model for the continuous sum. The continuous sum is very suspicious because it's like, I'll evaluate f of x dx at all the points from a to b, then add up the results. And we're like, oh, that's a continuum. Where do we put the plus sign? And then the fundamental theorem of calculus comes along and says, don't worry. We don't need a place to put the plus signs. We just need an antiderivative of the function. And then we just have to look at the endpoints. And that's the fundamental theorem of calculus, part 1. Oh, and this is where capital F is an antiderivative of little f. That is, we take capital F prime, we get F. First part of the fundamental theorem of calculus says that we can use an antiderivative to calculate a definite integral. The first part of the fundamental theorem of calculus says we can use an antiderivative to calculate a definite integral. Looking ahead to the second part, we just turn that around. We can use a definite integral to construct an antiderivative. That's the second part of the fundamental theorem of calculus. The new mechanics that we need to acquire is all that derivative stuff the other direction. We need to be able to calculate a general antiderivative. General antiderivative is the one with plus c. We'll also say indefinite integral or the one with plus c. Financial flow backwards today, so watch out. Classroom density is higher, stage left. So in the general antiderivative category, there's going to be as many general antiderivative formulas as there were derivative formulas, because we're going to take all our derivative formulas and just run them backwards, starting with our favorite. The integral of x to the n is 1 over n plus 1, x to the n plus 1. Better yet, x to the n plus 1 over n plus 1. Add 1 to the exponent, then divide by the exponents. Put plus c for your general antiderivative. So we're going to be finding area under a curve and above an interval by finding antiderivatives and plugging in the endpoints of the interval. So yesterday we had this trapezoid. I intended for it to be a triangle, but I did a 1/2 x instead of a 2x. So the picture of what's going on. We're going to be looking at the interval over from x equals 0 to x equals 2. This function starts off at y equals 4 and then decreases by 1. So it drops down to 3. And we're interested in the area under the curve and above this interval. So our height is given by this continuous function, 4 minus 1/2 x, and our width is from 0 to 2. Now, this was originally supposed to be a triangle, so we could just do a 1/2 base times height. It ended up being a trapezoid because I had the wrong slope. So we'll have to do the average of the heights multiplied by the base. So secretly, we already know that the area is a 1/2 half of 4 plus 3 times 2. Secretly, we already know the area. The reason we pick something which we already know the area is we want to see our method work on something that we are familiar with already. So the area using the definite integral a definite integral for the area will be the integral from 0 to 2 of our function 4 minus 1/2 x dx. We're thinking of the function as the height, that continuously variable height, and then dx is the little piece of the width on the denominator, on the interval. Area is length times width. We're going to evaluate 4 minus 1/2 x times dx at all the x values from 0 to 2 and add those up. That doesn't make any sense. It's a continuum. There's nowhere to put the plus signs. Fortunately, the fundamental theorem of calculus comes along and says, find the antiderivative of 4 minus 1/2 x. So add 1 to the exponent and then divide by the new exponent. Take an x, add 1 to the exponent, and divide by the new exponent. There's the antiderivative, and we're going to evaluate that from 0 to 2. This is just notation for us having already written the definite integral. Now we're going to plug in 2, plug in 0, and subtract the results. So I'm gonna have 4 times 2 minus a 1/4 2 squared. Then I'll have 4 times 0 minus a 1/4 times 0 squared. In this example, the 4 minus a half x, that's the little f of x. 4x minus a half x squared is the capital F at x. 4 times 2 minus a quarter of 2 squared, that's capital F at b. 4 times 0 minus a quarter 0 squared is capital F at a. Four times 2 is 8. 2 squared is 4, divided by 4 is 1. Minus 0, minus is plus 0. And we get 7, just like we expected. One of the skills that we need in place to play this particular game is the antiderivative skill. We need to learn to add 1 to the exponent and divide by the new exponent. We need to be able to read functions that can be written in that way. So that's what we're going to practice today. Any questions before we switch to the practice phase? How's everybody okay? I'm about to hand you a familiar set of functions. Actually, it's not familiar to you, it's familiar to me because I've used it over and over. You've only seen them once before, so you won't recognize it, but I will. Practice some moves. So let's take some time and practice finding some antiderivatives. This one says, find the general antiderivative. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And I'll do a slow scroll. I can't fit all 5 or 6 on one page. Let's take a few minutes and just discuss what's going on in some of these problems. There are some things that I want to point out. All these problems come down to add 1 to the exponent, divide by the new exponent. That's the procedure we're going to use. Add 1 to the exponent, divide by the new exponent. It's just about reading what the exponent is and adding 1 to it. And then, you know, some other algebraic stuff. So let's talk about the things that I observed. First one, no problem. 5 plus 1 is 6. 1 over 6. 1 6 x to the 6. Everybody 1 for 1 so far? Some people are like, oh, yeah, I am now. In the second one, we've got an x to the 3/5. So when we add 1 to the exponent, 3/5 plus 1 is 8/5. So I'll have an x to the 8/5. The reciprocal of the 1 over 8/5. 1/8 is 5/8. So the 1/, part just makes a reciprocal. So we don't want to go through the trouble of writing 1/8. We just want to read that as 5/8. We want to turn it over in our mind. If there was some coefficient in front of the x beforehand, like a 2, then I'd just do 5/8 times 2, 5/4, or 10/8. Maybe you don't like to simplify your fractions. In problem number 3, there was just 3 terms. We want to make sure that we read an x by itself as an x to the first and the 7 as an x to the 0. More importantly, we just want to know what happens to an x when we integrate it. The integral of x is a 1/2 x squared. The integral of a constant is just constant times x. But if you need a way to think about it with an nx to the n and x to the n plus 1 over n plus 1, read -3 to the x as -3x to the first. Add 1, 2, divide by the 2. Read 7 as 7x to the 0. Add 1 to get 1, divide by 1. So there's that one. In 1 over the square root of x, I rewrote that as x to the -1/2. This was just an algebraic rewrite. That's not doing any calculus stuff. That's just how we are reading 1 over the square root of x. So this is just an algebraic rewrite. That's why I still have an integral. That's why I still have a dx. We haven't done the calculus thing yet. So -1/2 plus 1 is 1/2. 1 over 1/2 is a 2. The reciprocal of 1/2 is 2. So that shows up as the coefficient. If you want to send this back to radical notation, you can write 2 root x plus c. Make sure that the root x ends over the x and does not go all the way over the plus c. It's one of the problems with radical notation. That's not super rad. So just be careful with your notation. As I've stated before, when you are writing answers for me, even if I give you the problem in radicals, you can answer in fraction exponents. You can always answer in fraction exponents if you prefer. Let's see, x to the 3.14. Just add 1 to the exponent and divide by the new exponent. The thing that I wanted to point out here is that 1 over 4.14 is a terrible number. Mixing decimals and fractions like this, look, it's gross. I want you to all look at that 1 over 4.14 and think, wow, that looks terrible. Doesn't it look terrible? It looks awful. If right now you're thinking it looks like just a fraction with a decimal in it. No, you need to think, ew, gross. Everybody look at that, make fun of it. Ew, what a terrible number. Doesn't matter. The problem is we can't express 1 over 4.14. We can't express that reciprocal without rounding that off. So when I write 0.242, that's been rounded off because it's 0.2415 and then a whole bunch of other stuff. So I just rounded it off. The only way to express that reciprocal is with this decimal and this fraction. So sometimes bad things happen. In this problem, I was just making a point. And then the last one, I combined a negative exponent and a radical. The thing that we want to recognize here is that when you have a fraction exponent, the denominator of that fraction exponent is the index of the radical. It tells you what kind of radical it is. So a 1/3 exponent is a cube root or a third root. So the denominator of the exponent is the index of the radical. Once again, we opened up with this algebraic rewrite. So I can see this as x to the n. X to the 2/3 in the denominator is x to the -2/3 in the numerator. Add 1 to the exponent, get 1/3. 6 divided by 1/3 means 6 times 3, 18. You can write that with a cube root or a 1/3 power. Any questions? So that was about 15 minutes on these 6 problems where it's just add 1 to the exponent, divide by a new exponent. You can assess how well you did on that yourself. That's going to do it for today. Reminder that there's no meeting tomorrow. So take tomorrow math off. You have your other classes. It's just me that's not going to be here. So don't be like, oh, skipping your English class and said, Leach said I didn't have to come to school. That's not what I'm saying. Math day off tomorrow. There'll be a discussion online. Everybody have a good day. See you Thursday. Thanks for playing.